Hello class, and welcome to video lecture number 3, all about standing waves. So as we talked about with wave interference, when you've got two waves happening at the same place at the same time, they interfere with each other. They add up or they cancel out. But sometimes when a wave bounces off of something, like a wall, and reflects back, it can interfere with itself. And sometimes when it does that, if the wavelength is just right, and if the frequency is just right, you get what's called a standing wave. So a standing wave is where you got spots called nodes and spots called antinodes. So you no longer see a wave moving. You see some spots that just don't move, called nodes, where you have absolutely no oscillation. And you have spots where there's lots of oscillation, called antinodes. So on my picture, this would be an antinode. This spot and this spot would be nodes. Nodes being where nothing's going on. See how it's not moving up or down? And the antinode is where everything is going on. Where the length of the string helps determine what wavelength of a wave can happen. If I have a wavelength that doesn't fit in this equation, I do not get a standing wave. I can have that wave happen, but it will not be a standing wave, where n is called the harmonic number, which is also the number of antinodes. So here we have 1, 2, 3 nodes, and 1, 2 antinodes. So n equals 2 here. So since this is the same string as before, but the n has gone up, that means the wavelength of this wave has gone down. They are two different standing wave patterns on the same string. All right, so remember that n is the number of antinodes, where L is a fixed length. We can't change it. And where the speed of a wave on the string is based off of the string. We cannot change the speed of a wave on that string. It's a property of that string itself. But if we know the length, and if we know the n, the harmonic number, the number of antinodes, then we can find the wavelength. So now we have wavelength. We know the speed, because it's based off the string. We can use this equation to find the frequency of this standing wave pattern. And as n goes up, so now it's 3, the wavelength has to go down, but L stays the same, V stays the same, which means that as n goes up, wavelength goes down, which means our frequency goes up. Now, if you remember, in music, the frequency is the note that you're playing, called the pitch. So, this string can only play certain notes. It can only play frequencies that you can get using these two equations. As n goes up, and 1, 2, 3, 4, 5, so on, that changes the wavelength, which changes the frequencies. So you can solve what possible notes can be played on your string. All right, now, a little bit of background knowledge. I know I got a lot here. Don't worry about it yet. Here, I'll even block some of it off. All right, so the note that is played is the frequency, called the pitch. Awesome. The frequency is going to be equal to the speed of the wave, which we cannot change, divided by the wavelength, which we can. The fundamental frequency, that is when n equals 1. That is when you have one antinode. That is the simplest standing wave pattern you can make. That is called the fundamental frequency. This is the note that your guitar plays when you pluck the string. It plays its fundamental. Now what about all those other n's? Well, when n equals 2, the frequency you get gives what's called the octave, for those of you that know music. For those of you that do not, don't worry about it yet. I'll explain that next video. Whenever you have an n of 3 or above, we can call it a harmonic. And technically, n equals 2, the octave, is also a harmonic, but we don't care about that. Whenever n is not 1, you are talking about the harmonics. So when you play a guitar string, you are getting the fundamental note loudest. So that's the note that is being played. But all those other possible frequencies are also ringing just very quietly in the background. Those are called the overtones or harmonics. Again, for those of you that know music. And the frequency of those harmonics will always be given by the fundamental frequency times the harmonic number. Yay! Which means, of course, that the octave, n equals 2, is twice the frequency as the original. N equals 3 is 3 times the original, and so on. Alright, so I've got a lot of stuff again. Cover it up for right now. Let us pretend that we have a 0.5 meter string. We want it to play a note of 440 hertz. Alright, so what do we know? We know our frequency. We know the length. We know that we want it to be the fundamental frequency, so we know what n is as well. Alright, well we know that the length of the string has to be 1/2 times n times wavelength. So we can solve for what the wavelength has to be, right? It's going to be 0.5 equals 1/2 times 1 equals wavelength. So the wavelength is 1. Now that we know the wavelength and we know the frequency, we can solve for the speed. So we need the speed of a wave on our string to be 440 meters per second. But how do we do that? As instrument makers, how do we make a string have a speed of 440 meters per second? Well, we got this nifty equation where the speed of a wave on a string is equal to the square root of the tension force divided by the linear density. Ooh, don't worry about it. Linear density is the total mass of the string divided by the total length of the string. So, we're just going to do this in parts. Let's pretend that my string has a mass of 0.001 kilograms. 1 gram. Just a made-up number. If we know the length is 0.5, and if we know the mass is 0.001, that means we can find the linear density to be 0.002. If we know that v is 440 meters per second, and if we know the linear density is 0.002, we can solve for the tension force. Go ahead and do that. Do you agree with me? You better. The tension force has to be 387.2 newtons. Which means that we can now make this instrument. You want to play a 440 hertz note. You want your string to be 0.5 meters. You know the mass of your string is 0.001. So you just need to tighten that string until the tension is 387.2 newtons. By doing that, you've set the speed of the wave at 440 meters per second, which means the fundamental frequency has to be 440 hertz, the note you want to play. What are you talking about, Mr. Sazzle? That was so much. Oh my god. It's okay. You'll be fine. In summary, when you're designing your instrument, you can choose what frequency you want. You can choose the length and mass of the string. If you know these things, you can solve for what wavelength you can have. If you know the wavelength, you can solve for the speed. And if you can solve for the speed, you can solve for the tension force. And that is all of the math that goes into designing a string instrument. All told, not too bad.